Our senior design project was initiated last summer at Texas A&M University. Our corporate sponsor 3M requested we design a novel device to connect large underground power cables together to improve upon the current industrial standard. The in-use connector operates by tiny bolts through an aluminum housing, clamping down and deforming the cable that has been placed inside. The unique thing about this connector is the shear bolt technology. When enough torque is applied to the clamping bolts, they shear off, preventing the connector from being over-tightened and ensuring proper installation. After doing preliminary research on the patents protecting the shear bolt connector, our team decided to take a different approach to the method of clamping. Two of the primary problems with the current technology lies in the lack of contact points between the cable and housing, in addition to the uneven stress distribution on the clamped cable. Our team realized we could solve both of these issues if we could design an electrical connector that secured the cable using a distributed multi-directional force instead of a unidirectional force.
Countless hours were spent researching methods to obtain this result. Finally, a rough design concept was produced. More research and calculations were performed to determine the critical dimensions, the optimal materials, and the ideal production method. Our final design was analyzed using finite element analysis and successfully passed the theoretical boundary. Our design was soon to be a reality.
The most difficult and time-consuming part of the process of bringing our design from an idea to reality was by far the manufacturing portion. Our team did most of the prototyping ourselves, spending almost 2 weeks in the machine shop. We used a variety of tools to complete our prototype, including lathes, mills, and CNC equipment. In addition to our own work, we acquired the services of a professional machinist to assist us in making several of the parts that had a very tight tolerance.
We concluded our semester by testing our design. Regulatory standards require the connector be able to withstand a tensile pull-out force of 40% of the cable's breaking strength and be able to withstand 1,000 current cycle tests. Tensile testing revealed our prototype to not quite perform up to standards, but further analysis showed several manufacturing errors that we believe contributed to the premature failure. We believe that with a few small modifications, our connector will be a viable alternative and possible improvement to the current shear bolt